We're going to go ahead and finish up with Chapter 20 today, and we're really just going to look at two different examples to do this. Our first example asks us if there are supposed to be 20% orange M&Ms. Suppose a bag of 122 M&Ms only has 21 that are orange. Does this contradict the company's 20% claim? Our first step is going to be to state our null and alternative hypotheses. Our null hypothesis is going to be what the company is claiming at 20%. So P equals 20%. Our alternative, because we're only trying to determine if it's a contradiction, we're not interested in if it's increased or decreased specifically, just that if it's different. So in this case, our alternative is that P is not equal to 20%. Then we move on to the next step, which is to state that we're going to do a one proportion z-test, and then check the conditions that allow us to do this test. So plausible independence. It seems that from bag to bag, they would be independent. We have our 10% condition. As long as more than 1,220 M&Ms are made, then we're good to go. Then we have the random. So each bag is filled randomly. And then our success fail. So in this particular case, our successes is 21, which is greater than or equal to 10, and our failures are 101, which is also greater than or equal to 10. So our conditions are all set. So then we move on to step 3, which is the mechanics. In the mechanics, we actually perform the calculation. So I need to figure out what my sample proportion is, and in this case it would be 21 out of 122, which is 0.172. Then I need to figure out my standard error, or standard deviation, and that would be 0.2 times 0.8 over 122, which is 0.036. So from here I calculate my z-score, so I would have my sample proportion minus my null hypothesis divided by my standard deviation, which is equal to a negative 0.7696. From here I have to calculate my p-value. Now this is where we get a little tricky because, and I'm going to draw a normal model down here, my z-score is at a negative 0.7696. Because my alternative is not equal to, that means I don't care if it's above or below. So it could be below this value, or I could go up here to a positive 0.7696 and say it could be above it. So because of that, when I calculate my p-value, I'm going to have to multiply it by 2 because I don't care if it's above or below. When I do calculate my p-value, I'm going to find the probability of this red area right here, that it is below the negative 0.7696. The probability that z is less than negative 0.7696 is equal to 0.221. Because it could also be above, I actually have to multiply this by 2. So I take this, multiply it by 2, and I get 0.442. This means that my p-value is equal to 0.442, or 44.2%. Now this is a really high p-value. So then when I write my conclusion, I will fail to reject my null hypothesis. So then my conclusion is written as, based on our sample, we failed to reject the null hypothesis with a high p-value of 0.442. There is not enough evidence to contradict the company's claim. So they could be wrong, but we don't have enough evidence to show that, so we failed to reject it, or we would retain our null hypothesis. So there's no reason to not believe that they actually do make 20% orange M&Ms. Our second example asks, a 1996 report claimed that 90% of all American homes have at least one smoke detector. Building inspectors visit 400 randomly selected homes and find that 376 have smoke detectors. Is this strong evidence that the local rate is higher than the national rate? So we have to go through our 4 steps. Again, our first step is our null hypothesis. Again, our null hypothesis is that there's nothing different, nothing interesting, nothing new. So that the current rate or proportion of people with smoke detectors is still 0.9 or 90%. we want to know if the local rate is higher than the national rate. So that means we're interested in our proportion being greater than 90%. Next, we move on to stating what model we're using, which is a one proportion z-test, and then we state our conditions to make sure that we can actually use this test. So we have random, and it was stated that they visited 400 randomly selected homes. Our 10% condition, so there are more than 4,000 homes in US. And then our success fail. So our successes is equal to 376, which is greater than or equal to 10, and our failures is equal to 24, which is also greater than or equal to 10. And it's the plausible independence. It is plausible to have each house be independent from the next. So if your neighbor only has one smoke detector, does not mean that you have to have one. Now that we've checked our assumptions and conditions, we can then move on to the mechanics. The mechanics, again, are where we perform our calculations. So our sample proportion, p-hat, is equal to 376 out of 400, which is 0.94. Our standard deviation is based off of our current model of 0.9 times 0.1 divided by 400, which is 0.015. Then we calculate our z-score. So z is equal to 0.94, our sample proportion, minus our null hypothesis, divided by our standard deviation, and we get a z-score of 2.67. Then from here we have to calculate our p-value. So I'm going to sketch the normal model to show the area that we need. Here would be a z-score of 2.67. My alternative is greater than 0.9, so I'm looking for greater than that, so just that area right there. So then that will give me a p-value of 0.0038, or 0.38%. Now this is a low p-value. With a low p-value, we reject our null hypothesis. So then in our fourth step, we can state our conclusion. And our conclusion says that based on our sample, we reject the null hypothesis with a low p-value of 0.0038. There is enough evidence to suggest that the proportion of homes with at least one smoke detector is greater than 90%. So then yes, the local rate would be higher than the national rate. All right, that is it for tonight. So I will see you guys tomorrow. Have a good night.